Hello, I'm Espiritu, and I work with the members on screen to complete the first design assignment of the semester. The task of our assignment is to maximize the kinetic energy of our two-stage rocket when it escapes the atmosphere. Each rocket stage has a different fuel consumption rate, fuel release speed, and engine mass. And we were challenged to distribute the fuel between the two stages in such a way that maximizes the kinetic energy while staying within a given budget of $3 million. The price of fuel and the stage of components are as seen on screen. The rocket is shot into the air with an initial velocity of 1 meter per second and experiences thrust force, drag force, and gravitational force. I focus mostly on building the FlexPDE model, the Python script, as well as the optimization of our grid search to produce the most accurate results. There are several physical constraints that directed our initial approach. Thrust for each stage is set to run only while there is fuel and works to accelerate the rocket by using Newton's third law reaction force and shooting fuel out the back end at a fast rate with incredible speed. The drag force is modeled with the quadratic damping relationship and is said to always oppose the motion of our rocket. It depends on the rocket's frontal area, drag coefficient, and the changing air density and velocity. The gravity force is calculated using Newton's universal law of gravitation, in which the force is determined by the masses of the two bodies and their distance from each other. Our simulation was modeled in Flex using Cartesian 1, where we looked to use a component method to describe the vector quantities. All grid parameters were kept at their defaults. Our simulation was halted when the rocket escapes the atmosphere, which is when this expression is met, which is at around a height of 44 kilometers. Our forces were implemented as shown on screen. We built the simulation step by step, starting with thrust, then drag, then gravity, isolating both drag and gravity and running simulations to ensure that it was built correctly. In order to verify the validity of our model, we plot thrust versus time, drag versus time, mass versus time, height versus time, and rho versus time. In this graph, we can see that thrust starts high and changes rapidly since stages fall off as soon as the fuel empties. In this graph, we can see that the drag is negative, except for when it's 0. It's low magnitude to start since the velocity starts at 1 and increases as velocity increases, but then drops since air density drops as well. In this graph, there are times when the mass decreases constantly. Then there are jumps which display times when the stages fall off. Rho versus time starts high and decreases as Ry decreases. We manipulated several initial parameters and predicted the results to ensure our model was built correctly. Increasing the drag coefficient showed that the drag scaled at a rate of 10 to the 5 compared to 10 to the 4 as expected. Increasing our rate of change of fuel mass for each stage showed a thrust that scaled at 10 to the 7 compared to 10 to the 6 as expected. The FlexPDE script was changed with string manipulation to include the %s in place of initial mass fuel in stage 1. From there, we were able to relate the initial fuel in stage 1 and stage 2 using the relationship on screen. It uses the cost to relate the two masses and assumes that you pay for all components of both stages no matter how we distribute the fuel. We also modified our code to output fuel mass in stage 1, kinetic energy throughout the rocket's flight, and the height at which the kinetic energy was measured. Our Python function plots the kinetic energy at our halt conditions for a series of masses ranging from 0 to 36,000 in stage 1. It also outputs the highest kinetic energy and the height and mass distribution by which that kinetic energy was measured. We reduced the range and the step size of our simulations to zoom in on the maxima seen in the scatter of the plot. This allows us to get an accurate mass distribution that produces the optimum kinetic energy at our halt condition. We also reduce the threshold associated with our define variables. In order to optimize our code, we incorporated the use of linear interpolation to account for the flex file failing to halt precisely at our set condition. It builds a line equation that connects 2 points and allows us to predict any point between these 2 points. And in conclusion, given a budget of $3 million, the most optimal fuel mass distribution to send the rocket out the atmosphere with the highest kinetic energy is about 29,522 kilograms in fuel tank 1 and 6,595.64 kilograms in fuel tank 2.